All right, welcome to a lecture covering section 6.5, Logarithmic Properties. So in section 6.3, we looked at and discussed just what is a logarithm in general. We looked at the definition of it and how it is used as the inverse of the exponential function. And then in 6.4, we went to the graph to see how these logarithmic functions act. And now we're going to start digging into more of the algebraic side of it and seeing what sorts of algebraic properties these logarithms have. And this is all building up to give us the tools to be able to solve logarithmic and exponential equations, which are then useful to begin to understand modeling real-world situations that show characteristics of being exponential or logarithmic. So let's go ahead and get going. Okay, so before we jump into the properties that are presented in this section, I just wanted to cover some of the basic properties of logarithms. Now, this is not in your textbook, so in every other textbook I've taught out of, they actually pull this out as a section on its own. And although we discussed these properties, it was done implicitly. So I felt like it was important to lay them out in a concise, condensed manner here, and I'm gonna talk about them briefly before we move into what's presented in the actual section itself. Okay, so I'm going to start out by just putting the definition that we learned in 6.3 on at the top of the screen here. So what we learned is that these two equations are equivalent. Log base b of x is y if and only if, that's a double arrow and that looks awful, sorry, b to the y is x. And if you can put that definition to memory, everything else that has to do with logarithms will really just flow directly from that definition. So, for example, if we look at the property log base, they're using base a here with this particular set of properties. Log base a of 1. Remember, this is asking what, let me get a different color, what can I raise a to get 1? Well, that has got to be 0 because a to the 0 power is equal to 1. Then we have log base a of a, and that's asking what can I raise a to make a, and obviously that's 1 because a to the first power is a. Then we have log base a of a to the x, and this says what can I raise a to raise a to the x power, and that has to be x because a to the x is equal to the a to the x. Now the last one is a little bit trickier. I'm actually going to come out, and what it says is when I raise a to a logarithm of the same base a, so this should be log base a of x, I get x, which is whatever is sitting in this position of the logarithm in the numerator. But let me back up a little bit and show you how we came to that, because it's a little trickier than the other four that we've looked at. So if we have log base b of x, it should be intuitive to state that that is equal to log base b of x. That's the reflexive property. It says anything is equal to itself. Now, if I wanted to change this to exponential form, I'd start at the base, raise to the is, and that equals the of. So that turns into b raised to the log base b of x is x. And that is the explanation for this particular property that I think is a little more insightful than what's on the screen here. So let's go ahead, now that we've recapped those and formalized them into a list, let's go ahead and move forward into the properties that are discussed in this section. Okay, so recall that we use the product rule of exponents. That's old material, prerequisite material actually for this course, to combine the product of exponents by adding. And what this says is, and I'll write it a little bit bigger, when I have exponents of the same base that I'm multiplying, so when I'm multiplying like bases, I add the exponents. And I'm not going to go into a lesson as to how that happens, because at this point we should know that, and it should be in our toolkit to use for the rest of the time you're studying mathematics. So now we also have a similar property for logarithms called the product rule for logarithms, which says that the logarithm of a product is equal to the sum of the logarithms, because logs are exponents, just written in a different form, and we multiply like bases and we add the exponents. We're going to use the inverse property to derive this particular product rule right here, which says when I'm taking log base b of some product, that says m times n there. That's the same exact thing as if I take the log of the first factor and add it to the log of the second factor. So I'm going to use this space down here to show you how that happens. So we're going to start with the premise that I'm going to let a lowercase m be the equivalent of log base b of m, uppercase m. And I'm going to let lowercase n be equal to log base b of uppercase n. So this uppercase m and n are the m and the m that show up as the product for that I'm trying to take the log of. So off to the side, if I start with m equals log base b of m, if I change that to exponential form, I start at the base, raise to the is, and equals the of, that says b to the m equals big M. And same thing with n equals log base b of capital N. Start at the base, raise to the is, equals the of. That says b raised to the nth power is capital N. So what I'm now going to do is I'm going to replace m and n in my logarithmic expression with b to the m and b to the nth. So that's what I have happening to the right-hand side. I'm actually going to white that out and rewrite it a little clearer here. Let me stick this to the board so it doesn't float around when I try to write on it. There we go. Okay, so if I replace capital M and capital N with b to the m, b to the n, I now have log base b of b to the m times b to the n. Okay? And my my product rule for exponents tells me that I can combine those into one exponent by adding the exponents. So that's going to equal log base b of b to the m plus n. Now, if I go back and use this property here that says when I'm taking the log of a particular base of that same base raised to an exponent, the answer is just that exponent. So this is asking, this particular expression is asking, what can I raise b to raise b to the m plus n? Well, it should be quite apparent that that is simply m plus n. And now I can go way back to the beginning and note that I had called lowercase m and n log base b of m, log base b of n. So this is equal to log base b of m uppercase plus log base b of n. So what we have successfully shown here is that when I start out with the log of a product, log base b of some product m times n, that is the same exact thing as taking log base b of m plus log base b of n. And that is called our product rule of logarithms. So if we're given a logarithm of a product, you can use that rule to write an equivalent sum of logarithms. And I'll show you that here. So this first one, I have log base 3 of 30 times x times 3x plus 4. So I have three factors here that I am multiplying. I'm multiplying 30, I'm multiplying x, and I'm multiplying 3x plus 4. I can expand this logarithm with log base 3 of 30 plus log base 3 of x plus, and I really should be using parentheses here, plus log base 3 of 3x plus 4. So I've turned all multiplication into addition of those logarithms there. Same thing here. I only have two factors this time. I have an 8 and a k that I'm multiplying. So to expand that, that would be log base b of 8 plus log base b of k. Simple enough. Okay, now let's look at the quotient rule. And our quotient rule is based off of our rule of exponents that says, oh, this is incorrect here. I will need to correct those notes for y'all. It says x to the a power divided by x to some b power, so I'm dividing like bases here. When I divide like bases, I subtract the exponents, a minus b. So there's my exponent rule for quotients. And we also have a quotient rule for logarithms. And now we're going to see how that shows up. So we're going to start with that same premise. We've got log base b of m divided by n, capital M divided by n. And I'm going to name lowercase m log base b of capital M and lowercase n log base b of capital N. So I can once again, off to the side, if I have m equals log base b of m, I can rewrite that as b to the m equals big M, and n equals log base b of n says b to the n is big N. So if I start out with log base b of capital M divided by capital N, I can replace my m and my n with b to the m and b to the n. Okay? And now I can use my exponent rule to say, well, that's got to be the same thing as log base b of b to the m minus n. And then I can say, well, if I have this expression here, it's really asking me, what can I raise b to raise b to the m minus n power? And that has to be equal to m minus n, but from the very beginning, we renamed m and n log base b of m minus log base b of n. So what this rule is telling you is that when you divide, or when you have the log of a quotient rather, that's the same thing as the log of the numerator subtracted by the log of the denominator. Okay, so we're just going to see this in action here. Okay, so I know from my property that we just discussed that this is the same thing as log base 2 of, okay, we've got 15x times x minus 1, and that's subtracted by log base 2 of 3x plus 4 times 2 minus x. Now, I believe that these problems just ask you to turn division into subtraction. But I want to point out that we can go further with this, because now I've got the log of a product with each of these. So I could expand this out further and say this is the same thing as, oops, I grabbed a white pen, hang on. This is the same thing as log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1. And that whole thing is being subtracted by log base 2 of 3x plus 4 plus log base 2 of 2 minus x. And the reason I left those inside a set of brackets is because this negative actually gets distributed to both of those. So my final expanded form of this would be log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1 minus log base 2 of 3x plus 4 minus log base 2 of 2 minus x. All right. Looking at this bottom one here, this is the same thing as log base 3 of 7x squared plus 21x minus log base 3 of 7x times x minus 1 times x minus 2. I can factor what's on the inside here. So that's the next step I'm going to take. This is log base 3 of, I can factor out a 7x, and I'm left with x plus 3. And that's being subtracted by log base 3 of 7 times x minus 1 times x minus 2. Okay, so now I'm just going to point out we still have products that we can expand. I have 3 factors in this first logarithm, and I have 4 factors in this second logarithm. So let me just remind you so I don't have to take up too much space. This negative is going to end up distributing to all those terms. So I'm just going to subtract each of those as I expand this out. So this is equivalent to log base 3 of 7 plus log base 3 of x plus log base 3 of x plus 3 minus log base 3 of 7 minus log base 3 of x minus log base 3 of x minus 1, minus, might be able to squeeze it in here, log base 3 of x minus 2. I just got it on there. Now we've got opposites that we can combine to make 0. Log base 3 of 7 minus log base 3 of 7. Log base 3 of x minus log base 3 of x. And I am left with log base 3 of x plus 3 minus log base 3 of x minus 1 minus log base 3 of x minus 2. Okay, the power rule for logarithms. So the power rule for logarithms says when I have some log of a base being raised to some exponential expression, what I can actually do, and I'm going to show you how this happens in a moment, what I can actually do is bring that power out front as a coefficient and multiply it by the logarithm. Okay, so let's take a look at this example here to see how that actually works. Log base b of x squared is the same thing as log base b of x times log base b of x. Well, we just learned from our product rule that's the same thing as log base b of x plus log base b of x, which says I have 2 log base b of x's. So notice the rule told us we could have skipped all this inside work here and just recognized that I can pull that exponent out front and multiply it by the logarithm. So let's take a look at these down at the bottom to show that example. I have log base 2 of x to the 5th. That is equivalent to bringing that exponent out front as the coefficient, and I am left with 5 times the log base 2 of x. Okay, the ln of x squared comes out front. Remember, ln is just log base e. I don't write log base e though. This is the same thing as 2 times the ln of x. Log base 3 of 25, why the heck is this in this section here? Because I can write log base 3 of 25 as log base 3 of 5 squared, which is the same thing as 2 times log base 3 of 5. And the ln of 1 over x squared is the same thing as the ln of x to the negative second power, which is the same thing as negative 2 times the ln of x. And then finally, we have 2 times the log of 3, log base 3 of 4. And it says to use the power rule to write a single logarithm with a leading coefficient of 1. So what they're asking us to do here is bring that 2 back up so that I have a coefficient of 1 on my logarithm. So we're working in reverse here. So this is the same thing as log base 3 of 4 squared, which is the equivalent of log base 3 of 16. Expanding logarithms. Okay, so what we were doing back on this page here and this page here and here, oh, no, here, here, we were doing what we call expanding logarithms. So to expand a logarithm completely, you have to meet 3 requirements. All logs of multiplication or of a product have been turned into addition of those logarithms. All logs of a quotient have been turned into subtraction, and all logs of an exponential expression have been turned into a coefficient multiplied by the log. Okay, so that's how you expand logarithms, is turning all multiplication into addition, all division into subtraction, and all logs of exponential expressions into a coefficient times the log. So here I start out with the ln of x to the 4th times y divided by 7. Okay, so the first thing I'm going to take care of is the quotient. This is the same thing as the ln of x to the 4th y minus the ln of 7, which is the same thing as the ln of x to the 4th plus the ln of y minus the ln of 7. And the only thing I have left to worry about is bringing that 4 out as a coefficient. So my final expanded form here is 4 times the ln of x plus the ln of y minus the ln of 7. So there's my final expanded form. Going to do the same thing with this next one. I start with log of, and that's common log, so understood base 10, x squared y cubed over z to the 4th. So that is the same thing as the log of x squared y cubed minus the log of z to the 4th, which is the same thing as the log of x squared plus the log of y cubed minus the log of z to the 4th, which is the same thing as 2 times the log of x plus 3 times the log of y minus 4 times the log of z. I'm now completely expanded here. It's like unpacking a box or putting a puzzle together, something like that. Okay, continuing, just expanding here. Here I have the log of the square root of x, and we don't ever want roots showing up in our logs. We want to change those to rational exponents. So this is the same thing as the log of x to the 1/2 power. That power comes out front, and I get 1/2 times the log of x. Here I have the ln of the cube root of x squared. That's the same thing as the ln of x to the 2/3 power, which is the same thing as 2/3 times the ln of x. Here I have log base 6 of my numerator, 64x cubed times 4x plus 1 minus the log of my denominator, log base 6 of 2x minus 1. And I have a product in that first log, so I can expand that out. Log base 6 of 64 plus log base 6 of x cubed plus log base 6 of 4x plus 1 minus log base 6 of 2x minus 1. And I'm going to come back and I'm going to call 64 2 to the 6th power. So my final expanded form here would be 6 times the log base 6 of 2 plus 3 times log base 6 of x plus log base 6 of 4x plus 1 minus log base 6 of 2x minus 1. And then finally, I have the ln of the numerator, which I'm going to rewrite as x minus 1 times 2x plus 1, all raised to the 1/2 power. That's where that square root is. And I subtract the ln of x squared minus 9. Okay, so first things first, I'm going to bring that 1/2 out, and I'm actually going to factor x squared minus 9. So it's the same thing as 1/2 times the ln of x minus 1 times, oh, that 2x minus 1 is squared. There we go. Times 2x minus 1 squared minus the ln of x plus 3 times x minus 3. Okay, so my next step is to say, okay, this is the same thing as 1/2 times the ln of x minus 1 plus the ln of 2x minus 1 squared minus the ln of x plus 3 plus the ln of x minus 3. Okay. This 2 comes out front here, and my negative gets distributed here and here. So here's where I am so far. 1/2 times the ln of x minus 1 plus 2 times the ln of 2x minus 1 minus the ln of x plus 3 minus the ln of x minus 3. And then the last thing that I'm going to do is distribute this 1/2 to each of those. So this is 1/2 ln of x minus 1. Now 1/2 of 2 is just 1, so this just becomes plus the ln of 2x minus 1 minus the ln of x plus 3 minus the ln of x minus 3. And that's it. Just like that. Okay, so here's my first answer, expanded, and here's my second. Okay, so we can also work backwards and start out with an expanded logarithm and condense it back down to a single logarithm. So the first thing I'm going to take care of is this addition right here. So I'm just going to turn that back into multiplication. So that's the same thing as log base 3 of 5 times 8, and then I'm subtracting log base 3 of 2. So far I have log base 3 of 40 minus log base 3 of 2. And now I'm going to take care of this subtraction by changing that back into division. So this is log base 3 of 40 over 2, which is finally equal to log base 3 of 20. So I packed it back into one logarithm with a coefficient of 1. That is condensing, so it's going in the exact opposite direction as expanding. So I'm just going to condense all these logarithms for you real quick. Okay, so I have, let's see, log of 3 minus the log of 4 is the same thing as the log of 3/4, and that is added to the log of 5/6, because I have 5 minus 6, so 5/6. So the log of 3/4 minus the log of 5/6, or plus the log of 5/6. And now I can change that addition into multiplication. So this is the log of 3/4 times 5/6, which is the same thing as the log of 15/24, which is the same thing as the log of 5/8. So I'm condensed. One single logarithm with a coefficient of 1. Okay, so I have plus and then a minus, so I'm going to put this back in as a product. And I'm also going to go ahead and put that 3 back up into the exponent there. Oh, and I'm going to put that 1/2 back up into the exponent. So I have log base 2 of, in my numerator, I have an x squared, and I have an x minus 1 to the 1/2 power, and that is being divided by an x plus 3 squared cubed. So I've got it all packed into one log, but I need to simplify this. So this is the same thing as log base 2 of x squared times the square root of x minus 1 over x plus 3 to the 6th power. All right. So this 2 needs to go up. Oh, let me box that for you. And it just takes practice with these logarithms. The better you know your properties, the easier this is. Okay, so I have subtraction I'm dealing with here, That 4 is going to go back up. I have addition to deal with here. That 1 over x goes back up. So my first condensing looks like the log of, let's see, x squared over x plus 5 to the 4th power. And then that's plus the log of 3x plus 5 to the 1 over x power. So I'm going to do one more simplification before I put these together. So this is log of x squared over x plus 5 to the 4th plus the log of the x root. That's the 1 over x power there, the x root of 3x plus 5. And now I just have the addition. So this is the same thing as the log of, I'm going to write this a particular way and then do another simplification step. This is x squared over x plus 5 to the 4th power, and that's being multiplied by the x root of 3x plus 5, and that's over understood 1. So my final condensed logarithm is the log of x squared times the x root of 3x plus 5, all divided by x plus 5 to the 4th power. Okay. Log of 5 plus 0.5, log of x minus, okay, so that 0.5 goes up. And I'm subtracting this log of x plus 7, so that's going to go in the denominator, and then I'm adding, and that's going to go up as well. Okay, so log of, in my numerator, I've got 5 times x to the 0.5 is 1/2 power times x minus 1 cubed, all being divided by 7x minus 1. Okay, the only thing I have left to do here is to change that 1/2 power back into a root. Log of 5 times the square root of x times x minus 1 cubed over 7x minus 1. There we go. And you notice I'm skipping steps now for the sake of room on the screen, and because as you move through more and more of these problems, you can do more of it in your mind without having to write out every single little step. All right, this 4 has to go back on the entire logarithm there. The 3 goes back on the x, and those are in my numerator, and then I'm dividing by 2x plus 3, so that goes down in my denominator. So I have the log of my numerator. I have I have x with that cube back on it, but then that 4 goes back on it as well. And that's times x plus 5 with that for an exponent, and that is being divided by 2x plus 3. So my simplified version of this is log of x to the 12th times x plus 5 to the 4th all over 2x plus 3. There we go. Okay, our last property for this section is called the change of base formula. And the reason we need this is because most calculators, and your TI-84 or 83 calculator specifically, only work in two bases, base 10, which is the common log, and base E, which is the natural log. So we need to have a way of being able to write the log of any base as either base 10 or base E so that we can plug it into our calculator. So we're going to start with this premise that we're going to start with log base n of b to the y, and we're going to call y log base b of m. Okay, so let me actually white this out and show you how this happened. That's a little bit of a leap there. Okay, and stick that to the board. Okay, so if I replace y with log base b of m, I have log base n of b raised to the log base b of m. So all I've done is replaced y with log base b of m. And inside the parentheses is that property. When I raise a base to a logarithm of that same base, it's just that thing that you're taking the log of. So this becomes log base n of m. And let me just go back. That's this property here that gives you that. Back here is this property right here. A base raised to the log of the same base is just that thing you're taking the log of. So that just all becomes capital M there. And now, from that, let's see, log base n, that comes log base n of m. So right now I'm to the point where log base n of b to the y power is equal to log base n of m. I can now bring that y out front as a coefficient. So y times log base n of b equals log base n of m. And I can divide log base n of b off of both sides. And that leaves me with the y equals log base n of m divided by log base n of b. However, I noted at the very beginning that my y, which all I'm left with on the left-hand side now is y, is actually equal to log base b of m. So what I finally get is that log base b of m is equal to log base n of m over log base n of b. So let me point this out. What we've done is taken the log of some base b of m, and I have changed it into the log of a new base n of m divided by log of that same new base of b. So this is how we change bases. Now you may choose to have that base be 10, or you can choose to have it be e. It doesn't matter. You're going to get the same thing either way you put it into your calculator. So here are rules laid out that I just showed you how we arrived at. So let me show you how we use this. If we start out with log base 5 of 3, I now know that that's the same thing as the common log of 3 divided by the common log of 5. Or that's the same thing as the natural log of 3 divided by the natural log of 5. Now be careful putting this into your calculator. This is where students mess up. When I put, we'll just use the natural log one since it's the one all the way to the right. When you put this into your calculator, you're going to hit the ln button, and it's going to open a set of parentheses. You're going to need to type in 3, close those parentheses, then hit your division symbol, then hit your ln button again. It's going to open parentheses, type in 5, close your parentheses there. So when I plug that into my calculator, and you can use common log. It does not matter at this point, as long as they're the same base. So let's see, ln of 3 divided by the ln of 5 is approximately, and usually we round to the 4th decimal place with this. It is approximately 0.6826. Okay. Here we go. It says to use natural logarithms, but you can use common log too. I'll show you. Log base 0.5 of 8 is the same thing as the log of 8 divided by the log of 0.5. And when I put that into my calculator, I get that as approximately, let's see, log of 8 divided by the log of 0.5. I get, and actually it's exactly, I don't need my approximate symbol, that equals -3. Okay, evaluate log base 2 of 10. Log base 2 of 10 is the same thing as the log of 10 divided by the log of 2. The log of 10 is just 1, because that's saying what can I raise 10 to make 10? So that's really just 1 over the log of 2. That's what I'm going to put into my calculator here. 1 divided by the log of 2. I get approximately 3.3219. And then finally, log base 5 of 100. That's the log of 100 divided by the log of 5. The log of 100 is 2 divided by the log of 5, and that gives me approximately 2.8614. All right, that's all I've got for you on the properties of logarithms. Hope this was helpful.